So we finished yesterday talking about chemistry as just a generic science, and we said that it originated with this alchemy, right? And so chemistry is all about measuring things, observing things, collecting data off of matter. So then we have to kind of figure out, all right, what properties can we measure with matter? And that's where we're going to start off with today. We're going to start off talking about physical properties. So physical properties are things that can be measured or observed very clearly. And the key thing with a physical property is you aren't changing the matter that you're looking at, right? If you measure a piece of lumber, you're not cutting it up, you're just measuring the length of it. So let's make a note that this is without changing that matter into a new type of matter. All right, does anybody want to help me compile a list of some physical properties? What are things that we can measure? Not everybody all at once. Yeah? Size? Yeah, so exactly. We could do something like length, right? What's another one? Yep. Yeah, something's mass. So mass is another way of describing how much something weighs. Is mass and weight always going to be the same thing? No, and we'll talk more about that later. If I'm in space, right, I don't have any apparent weight. I float around, but I do have mass. So we do have to describe mass and weight a little bit differently. What's another thing? Yep. Volume. That's another big one. So volume is basically how much space you take up. Does anybody have another one? Density? Yeah, so density is important, and that's related to our first lab that we're doing with pennies. How do we measure density? Does anybody know? Mass over volume, and we'll review that a little bit too in case some people are unfamiliar with it. What's another thing we can measure? Temperature. Do scientists like to measure things in Fahrenheit? No. We're kind of oddballs. Does anybody watch the show Archer? Yeah. They had a joke on there where they were saying the only countries that still use the Fahrenheit system are the US and Libya and Burma. And it's like, wow, we're in the same pool as Libya and Burma. The rest of the world uses Celsius. So we're going to use Celsius or Kelvin in this class, and we'll talk about how to define things in terms of Kelvin later, because a lot of people aren't familiar with that. There are a few other physical properties that we can measure. So we can measure things like color. It's pretty easy to observe the color of things unless you're colorblind. Taste. We're not going to taste our experiments, but if you're a food chemist, you might. You can measure things like boiling point. You can measure things like freezing point. You can also measure things like hardness. Does anybody know what the hardest thing is on our planet? Diamond, right? So the only thing you can use to cut diamonds are other diamonds, right? So when you're polishing a diamond, the wheel that they actually use to polish it has a bunch of powdered diamond on it. So we can measure the hardness of things too. If you go on to geology classes, you'll cover that in a lot more detail.
I thought they used water.
They use water too to disperse the heat. Whenever you have that wheel spinning really fast, it creates a huge amount of friction, so they typically wet it with some water just to cool everything down. Yeah, that's a good point. The other thing we can measure too is odor, or you can at least observe it, apparently. And all of these are important properties that you can observe or measure, but you aren't changing the substance that you're looking at, right? If you're measuring the taste, or if you're tasting something, you're not changing it, you're just ingesting it, essentially. All right, so now let's kind of go back to that mass versus weight argument. And I did want to describe this in a little bit more detail. So mass is an intrinsic property. where weight depends on gravity. So typically scientists prefer to use the term mass. Mass and weight are interchangeable on Earth, but as soon as you leave Earth or you go into outer space, weight doesn't really mean anything, right? It doesn't mean what it means on our planet. So how do we measure mass? If I were to go on my scale at home, my scale typically would show my mass in pounds, right? Some scales you can change that to kilograms. So in the US, we use pounds. And that's abbreviated LBS. However, everyone else measures it slightly differently. How does the rest of the world measure mass? What units do they use? Kilograms or grams, right? So in this case, we use grams or kilograms. If you're in a physics class, chances are the base unit that they use is kilograms, but if you're in a chemistry class, we usually use grams. We don't deal with things that are that heavy very often. All right, and I like to always compare these to things that I'm familiar with, so we have to come up with a good estimate. Most people in the US aren't that familiar with grams. However, a cube of sugar is about 4 grams. So if you hear somebody say, hey, this weighs 10 grams, you can imagine 2.5 cubes of sugar, right? It weighs about that much. I like coming up with some simple estimators. That way it's a lot easier to approximate the mass or length of something. The other thing that's really important is that scientists often use prefixes. And in the case of grams, we made a note that most of the world measures things in kilograms. What does kilo mean? 1,000, right? So we use prefixes all the time in chemistry and physics in order to describe quantities that are either really, really large or really, really small. So they're deviating from that standard base unit. We'll go over all the prefixes that you need to know for this class, and I'll give you a handout too, but I'm going to trim them down to the core essential prefixes that you should know. All right, so now let's switch gears and talk about volume. That was one of the other important physical properties. And volume is the amount of area that you displace. And chemists like to measure volume using a couple different techniques. One is that we measure it in milliliters. How many of you guys are familiar with milliliters? So if you pick up your Nalgene bottle, right, those standard size Nalgene bottles, that's 1 liter. What does a milliliter probably mean? It's probably something a lot smaller than a liter. It's 1/1000th of a liter. So your Nalgene has about 1,000 milliliters of volume in there. So scientists like to use milliliters. And we abbreviate this lowercase m, capital L, and we use this when measuring liquids. For solids, we have to use something a little bit different. Typically with solids, what you use is centimeters cubed. However, one really, really nice thing about this is that they are the exact same. So if you work in a hospital setting, you might see something listed in a volume of cc, that's cubic centimeter or centimeter cubed. It's interchangeable with milliliters. So that's an important thing to keep track of. At least for water it is. So if you think about a centimeter cubed, really all it is this idea that if you had a cube of water, it'd be 1 centimeter tall, 1 centimeter wide, and 1 centimeter thick. And for water, 1 centimeter cubed, is equal to 1 milliliter. And like I said, you might see centimeter cube abbreviated as cc. It really doesn't matter how you show it. However, most scientists prefer to write it as centimeter cube to avoid any confusion there. Are there any questions with mass and volume? All right. Let me know if I'm going too fast or if I'm going too slow. You can also let me know too. So let's switch gears and talk about density. Density is a really important measure in chemistry. It tells you a lot about the compound or the molecule that you're dealing with. And it's usually measured by taking your mass, dividing it by your volume. And in this case, our mass unit that we normally use as a chemist is going to be what? Is it grams or kilograms? Probably grams. If you're a physicist, you might use kilograms, but chemists like to use grams. So in this case, this is normally measured in grams. And then the volume we just discussed, this is usually measured in milliliters or in centimeters cubed. It really doesn't matter. So it's this ratio of grams to volume, or mass to volume. One thing that's important to remember too is that this is a really valuable tool. You can change this around using simple math. So if density equals mass over volume, what would mass equal? Yeah, density times volume. So you can rearrange this. What if we want to find volume? Yeah, mass over density. So you can use simple basic math to change this around and solve for whatever variable you want in this equation. It's pretty handy. And like I said, for solids, we typically measure that volume in centimeter cubed, and for liquids, we normally measure it in milliliters. So let's take a look at a handful of examples. All right, the first example is the density of water. Does anybody know what the density of water is? What do you think? 1. Yeah, it's kind of our baseline standard for density. So water at room temperature, at least, is about 1.00 grams per milliliter. It's a really easy density to remember. However, I am going to make a little bit of a note here, and I'll say at room temp. Do you think water has the same density at all temperatures? No. Yeah, exactly. If we take the density of ice, ice has a density of 0.915 grams per milliliter. So density is kind of weird. It depends a lot on the temperature, which explains why ice floats, right? It's got a lower density than water itself. Water is a super weird compound. Most compounds, if you freeze them, actually have a higher density and will sink. Water is the opposite and will float. If you go on and take oceanography, it's a super important part of our overall planet. The fact that ice floats is key to all of our ecosystems, or that ice floats, I should say. There are some compounds with really, really weird densities. So let's do an example. Let's do mercury, not the planet, but the element. So mercury, has anybody ever seen it before? What does it look like? It's a liquid metal, right? It looks like liquid silver. If you've ever seen, what was it, Terminator 2? It kind of looks like that stuff. The density for mercury is 13.53 grams per 1 milliliter. The craziest thing with mercury is you can get a bowl of it, and you can take a quarter, and you can throw it into that bowl, and your quarter will float on the liquid. Mercury is a very, very weird liquid that way. There are some ultra-dense liquids and ultra-dense solids. What is an ultra-dense solid that you guys know of? Something that's really, really dense. Which one? Uranium is super duper heavy. If you've worked in the military at all, Oftentimes the armor plating on the outside of tanks or on the outside of vehicles is depleted uranium. It's super duper heavy. It is not easy to pick up. Does anybody know another one? Which one? Platinum is super heavy. Gold, lead, things like that. Typically it's the heavier elements. If you look at the periodic table over there, typically the further down you go on the periodic table, the heavier things get in terms of their density. So gold is a good example of something that's really dense. I'm not sure if many of you have picked up a big piece of gold, but it's surprisingly heavy. All right, so we've talked a lot about physical properties. These are all things we can measure, but we're not changing anything. We do have to investigate chemical properties a lot in this class too. So we'll change gears and talk about chemical properties. So chemical properties are different from physical properties. This describes change. So we are going to change matter. So it describes how matter reacts with other types of matter. And the key thing is that this involves change. So typically when we're thinking about physical properties, there's no change. Chemical change, there is a change. So let's take a look at some examples of chemical properties. Let's say we have a big hunk of iron and we leave it out in the front yard for a few weeks. What will happen to that chunk of iron? It'll rust, right? So iron will change into iron oxide. It will react with the air in the environment and undergo a chemical change. All right, carbon is my favorite element. It is the building block of all life, pretty much. And let's say we've got carbon in the form of a tree, and then we put a match to it. What will happen? What will we make? Fire and ash, right? So I'll just put down ash and heat. Silver is another interesting one. Silver, if you've got fancy silverware that's actually made of silver, what happens if you leave it in your drawer for a long time? It'll tarnish, right? And then you have to rub it off. My grandma made me do it all the time, and it would drive me crazy. So tarnish. And then another cool one is nitroglycerin. What happens if you hit this with a hammer? It'll explode. Does anybody know who was the key scientist that started working with nitroglycerin? He turned it into dynamite.
Nobel?
Yeah, Nobel. So how many of you guys have heard of the Nobel Prize? So Alfred Nobel realized that nitroglycerin could be really, really useful as an explosive. Let's say you're digging a tunnel and you want to blast away a bunch of rock. However, if you've got a wagon full of pure nitroglycerin, that's going to be a pain to transport, right? You run into a bump, your wagon explodes, you've got a big crater in the ground. So he found that you could take nitroglycerin, this compound, and mix it with something called diatomaceous earth, which is essentially clay, and it makes it a lot less reactive. That way it doesn't accidentally explode all the time on you. Alfred Nobel was actually ostracized a lot during his life. People thought that he was basically this chemist that made weapons of mass destruction. A lot of people blamed him for all of the wars that were being fought and things like that. The poor guy was super duper depressed. And so what did he make to alleviate his guilt? The Nobel Prizes, right? So he basically gave all of his money into the Nobel Foundation, and every year they have a prize for physics, chemistry, medicine, literature, and then the Peace Prize too. And that endowment that he set up with this experiment actually is living to this day, and it's, I think, growing to many billions of dollars. So it's kind of this weird history of chemistry. All right, so let's talk about chemical versus physical change, and then try to predict whether this change is going to be a chemical change or a physical change. All right, so let's say we fry an egg. What do you guys think? Is that going to be a chemical or a physical change? Physical? Chemical? Does anybody want to say why they think it's a chemical change? What do you think?
Because when you fry it, it changes the makeup of the, like how everything is together.
Yeah. What were you going to say? Yeah, somebody's taking biology. So whenever you apply heat to something like an egg, you're actually changing the layout of the proteins in that egg, and you're changing it in a molecular way. So you're making and breaking bonds, and we're going to spend a lot of time talking about bonds. But frying an egg is a good example of a chemical change. All right, let's do another one. What about freezing water? Check with your neighbor and see if you agree. All right, let's see a show of hands. Raise your hand if you think it's a physical change. Ah, good. Why is it a physical change?
It's still water, it's just changing the shape.
Yeah, it's still water. All we've done is change the temperature, right? We haven't altered the water itself. So this is a good example of a physical change. Another good thing to keep in mind is oftentimes physical changes are reversible, right? You can freeze water and unfreeze it and go back and forth a bunch. If you fry an egg, can't unfry it, right? It's kind of stuck at that point. Let's do another one. Crushing rock. What do you guys think? Raise your hand if you think it's a physical change. Why do you think it's a physical change? Does anyone want to help me?
It's just less rock.
It's just less rock. You're changing the size of the rock. It's still rock, it's just smaller rock. Okay, so that's a physical change. All right, let's do another one. Let's do digesting food. What do you guys think? Chemical? Hopefully. If you eat something and it comes out the exact same way it went in, you should probably see a doctor. So this is a good example of a chemical change. Whenever you digest food, you're basically breaking down all of the bonds in that food and getting energy from those bonds. Food is really just an elaborate energy storage system. How do we measure the energy in food? Calories, right? So if you pick up your groceries, you can look on the back and see how much energy is stored in that specific food product. All right, let's do another one. Water evaporating. What do you guys think? Chemical, physical? Talk about it with your neighbor. Try to argue.
He's supposed to argue against
All right, let's see a show of hands again. Raise your hand for physical change. Raise your hand for chemical change. Couple. All right, think about it this way. If water evaporates, what happens to it? It turns into a gas. That water goes up into the sky, can collect as a cloud, and then what happens with clouds? They can rain, right? So it's still just water. It's just water in a different form, right? So when you heat up water, you can change it to a gas as steam, but it's still water. So in this case, this would be a good example of a physical change, although it's an abstract type of physical change. Does that make sense? Okay. So let's go on and classify matter a little bit. I know this is going to sound kind of silly, but we have to describe matter as what three types? Yeah, liquid, gas, and solid. So this is stuff we normally learned pretty early on. So three types of matter. These are the three main ones. If you go on into higher level physics, there's things like plasmas, which are super excited gases. A common example of a plasma is fire, right? How do we describe fire? Is it a solid? Is it a liquid? Is it a gas? Well, it's a super excited gas. We're not going to talk about that. It's outside of the scope of this course. So solids, liquids, and gases. All right, and let's make some observations. So with solids, what happens if you put it into a container? It just sits there, right? So it retains its shape. A liquid, on the other hand, will do what when you put it into a container? Yeah, it'll take the shape of the container. It'll flow. So it takes the shape and then a gas, what will a gas do? It'll fill up the entire container, right? So if I fill up my Nalgene with gas, the entire Nalgene bottle's full. The gas doesn't settle on the bottom. It'll just occupy the entire volume. So it assumes the shape and volume. All right, and then if we think about other features with a solid doesn't flow well, right? If I try to take a rock and roll it, yeah, you might get a couple of rolls, but it's not going to just randomly flow down a hill, right? So a solid doesn't flow, at least not well. There are certain situations where it will, like landslides and stuff like that, but that's more of an oddity. Liquids, on the other hand, flow super well. And then last but not least, a gas flows super well. In fact, a gas, if I were to spray perfume up here, chances are those of you in the back would smell it within a minute or so, right? Gases like to occupy all of the room that they're in, and they'll disperse throughout the entire room. And then the other thing we can measure too is compression. Is it very easy to compress a solid? No. So not easy to compress. Liquids are also not very easy to compress. And then last but not least, can we compress gas? Yeah, absolutely. If you've gone scuba diving, you've had a compressed gas cylinder on your back. So gas tanks are very, very common, and it is easy to compress. All right, and oftentimes if we're looking at matter, whether it's a solid, liquid, or a gas, it's not pure. It could be a mixture, or it could be some oddball thing. So let's try to classify various types of mixtures. So I'm going to make this into a flowchart. And at the top of our flowchart, we've got just generic matter. Solid, liquid, or gas, doesn't matter. And we can divide this into pure substances and mixtures. All right, pure substances. We actually have to subdivide this even further. There are two different types of pure substances. There's one type where it's just an element. And then on the other side, you've got compounds or molecules. What do you guys think the difference is? Yeah, exactly. A molecule is made up of more than one element. It has covalent bonds. So if we look at the periodic table over there, right, that one in the top right-hand corner, the He, that stands for helium, right? Helium gas, you fill a balloon with it, that balloon's full of just helium atoms, right? Where water is made up of what? Hydrogen and oxygen, right? So water would be a good example of a compound where helium would be a good example of an element. So let's make a note of that. It is one atom, and we said an example would be helium. Helium doesn't really like to interact with any other elements. It has a special name called a Nobel gas. It doesn't want to really do anything. It's pretty happy on its own. Where compounds or molecules have bonded atoms. And we'll talk about what bonds mean later. And then we said an example of this would be water. And we said that water is made up of hydrogen and oxygen. With mixtures too, we have, yep?
So would like O2 be an element or a compound? 'Cause
It really depends on who you ask with something like that. So typically if you've got something made up of only one element, so O2 for example, it only has oxygen, people will call that elemental oxygen, even though it has a bond.
okay.
Does that make sense? There are some situations where you run into that. With mixtures, we can classify these as two different types as well. We have homogeneous and then we have heterogeneous. All right, so we've got some prefixes here. What does homo mean? The same. Hetero means different, right? So what do you guys think a homogeneous mixture is? Yeah, it's mixed pretty evenly, right? It's the same throughout, is another way of thinking about it. A good example of this would be something like salt water, right? If you get a mixture of salt water, that salt water is going to be the same all throughout the container. A heterogeneous mixture means that it's different throughout. Oftentimes people don't even think of these as mixtures, right? Because it's not a mixture in the way we normally think of a mixture. A good example of a heterogeneous mixture might be a pizza, right? Pizza has a bunch of different toppings. It's not even throughout. You've got one area that's crust, one area that's sauce, one area that's maybe cheese or pepperoni. So it is different throughout. So there will be probably on the first exam some mixtures that I have up here, or up on the exam, and then I ask you to classify them as homogeneous or heterogeneous. Yep?
So would something that like separates, like if you put it in the same jar, would that be hetero?
That's a good question. If it's evenly mixed at the time you're looking at it, you would call it a homogeneous mixture. But if it does separate out, you would call it heterogeneous. Yeah. All right, so let's take a look at the ultimate building block of matter, the atom. Are most of you guys familiar with the term atom? Atom is the ultimate building block of everything around us, right? What is an atom? Does anybody want to help me describe it? It's the smallest part of something. I think that's a great explanation, actually. So it's a fundamental building block of matter. And it's basically the smallest pieces that make up matter. If you go on to physics, you'll talk about subatomic particles. We're not going to talk about those in very much detail, at least not until we delve further into the atom. So for right now, atoms, as far as we are concerned, are the smallest building blocks that make up everything, right? And we said that elements are the things that you see on the periodic table. Each one of those squares represents a unique element. Today we have about 118 unique elements that have been identified and characterized. Typically, when you get into the ones above like 100-ish, they aren't super stable. Does anybody know why? Their weight, they're super duper radioactive. They tend to fall apart into smaller elements. So the really, really heavy elements aren't as common as the lighter ones. What's the most common element in our universe? Does anybody know? Hydrogen, right? Typically the most abundant elements are going to be the lightest ones on the periodic table. So elements, you can think of them as a few different ways. We said a good example would be something like helium. If you've got helium gas, it's basically just a bunch of helium atoms flying around as a gaseous form. Where we said that a compound or a molecule would be something like water. And water, we said, is made up of a couple different elements. We've got two hydrogens that are bonded to an oxygen, right? And in this case, we've got a 2-to-1 ratio of hydrogens to oxygens making up each water molecule, right? So in this case, this is a fixed ratio of bonded atoms. And they cannot be physically separated. So if I take some scissors, I can't go in and I can't cut hydrogen away from oxygen, right? We can do that chemically, and some of you may have seen the space shuttle launches a few years back. I know they've been retired, but did you guys know that the space shuttle was actually launched using hydrogen and oxygen as the fuel source? Basically what they would take is a giant container of liquid oxygen and liquid hydrogen in that big orange tank. They would mix them together, light a match, and then boom, it turns into water, right? It's an incredibly powerful propellant.
Yep. Like a solid fuel booster, right?
Yeah, they did have some solid fuel boosters, but the main propellant that they used on the space shuttle was hydrogen and oxygen. If you're interested in space stuff at all, there's one reason that they shifted away from the space shuttle program. This is actually really, really dangerous, transporting that much liquid hydrogen and oxygen. If you had to abort a launch, all of a sudden you had this giant bomb that you had to basically let all the gas escape from. Otherwise, it was just waiting to explode, more or less. So it's one thing that they're looking at a lot. If you've been following SpaceX, they use solid fuel rockets. Was there another question back here?
I think it's the same. So what you mean by fixed ratio, that just means that the second part of it, it means that it can't be physically separated.
Yeah, exactly. It means there are two hydrogens for each oxygen. Oftentimes we describe water as H2O. With helium, we don't say He and then a number, right? Because it's assumed to be an infinite amount or a relatively infinite amount in the container it occupies, right? So there's no fixed ratio of helium atoms. It's whatever amount of helium can fit in there. Yep. All right, so let's talk about how we represent atoms and molecules and things like that. And lucky for us, in almost all of the rooms on, at least in this building, we've got that fancy table over there called the periodic table of elements. That's the easiest way to describe an element, right? Is you go to the table, you look at it, and you try to find what symbol represents the element you're talking about. If you look at them, some of them aren't super intuitive, right? So if you look at Hg on there, does anybody see where that is? It's number 80. It's in green. What does Hg stand for? Does anybody know? Mercury, right? So it's not always the same way that we spell things out. Oftentimes they're based off of the Latin names that the elements were called a long time ago. So we will talk about that in a lot more detail, but we're going to use the periodic table all throughout this class. So typically, we'll have that available for exams, or I should say we will always have that available for exams. All right, so what do we do if we have a molecule? And so let's do a simple one. Let's do hydrochloric acid. Hydrochloric acid is the stuff that's in your gut, right? So when you digest food, it's oftentimes being broken down at least partially by hydrochloric acid in your stomach. If you've ever thrown up, chances are you've tasted that nasty acidic flavor that comes up along with whatever food. So now if we look at hydrochloric acid, we have to ask ourselves, as chemists, how can we represent this using symbols? And oftentimes we can do this by breaking apart the word. So we've got hydro here. What do you think hydro is? Hydrogen, right? So in this case, we've got a hydrogen. And then we've got this chloric over here. Chlorine, right? So if you're familiar with the periodic table, Cl is number 17 over there. And hydrochloric acid is just represented as HCl, right? So in this case, is it an element or a molecule? It's a molecule, right? It's a 1-to-1 ratio of hydrogen to chlorine. And we'll talk more about acids and bases later on this term. All right, let's do another one. Let's do argon. If we look at the periodic table, does anybody know what symbol argon might be? AR, right? That one's a lot easier. It doesn't have some funky Latin name. So in this case, argon is represented by the symbol AR. And is this an element or a molecule? Element, right? Argon is often found in signs, right? So if you've ever gone to Las Vegas and seen all of the signs that they have, those are all made up of those gases on the right-hand side of the periodic table. They'll take things like neon, argon, or even some of the heavier gases. They put electricity through them. When they excite those molecules, they emit a really cool color. So that's why we call them neon signs, is they're all based off of the same type of principles. All right, let's do another one. Let's do methane. Does anybody know where we find methane? What's that? Poop? Yeah, if you've ever been to a cattle farm, produces a lot of methane. Bacteria, at least a good portion of our bacteria, will actually digest organic molecules and convert it into methane. It's a big problem. Methane's a potent greenhouse gas, a lot more potent than CO2, and it's argued that the cattle production in the United States actually emits more greenhouse gas than all of the cars in the United States. There is actually a lot of work going on right now to feed cattle enzymes that will actually prevent them from producing methane, but that's still kind of in experimental trials right now. So methane, we have to describe this using chemical symbols. Methane is a carbon-based compound. It's made up of 1 carbon and 4 hydrogens. And to show this, we don't write CHHHHH. We just abbreviate it as CH4, which means for every 1 carbon, we have 4 hydrogens attached to it. Is this going to be a compound or an element? Compound, exactly. It's a fixed ratio. You can say compound or molecule. It really doesn't matter. I use them interchangeably all the time. I know it can be confusing for people at first. Methane is also found in natural gas. It's often used in your homes to heat or to heat your water. Are there any questions with this? One thing that students get confused on with things like methane is how to write the 4, right? So if we write the 4, it needs to be subscript, meaning it's a little number, and it needs to be at the bottom, not on the top. So anytime you have this fixed ratio, try to include that number in the bottom right-hand corner next to the element it represents. Why don't we have a 1 next to carbon? It's assumed, right? You're just wasting time at that point. So we don't have to write C1H4, we just do CH4. Yep.
Is there any reason why we don't do
We'll talk about that. There is typically a standard order. Normally, hydrogen comes last, with a handful of exceptions. There are always exceptions in chemistry. Yep.
How are elements made? 'Cause I know like we made technetium, but I don't know. Like, I know it's like adding protons, but
That's a good question. So there are natural elements that are just found everywhere on our planet, and then there are unnatural elements. The unnatural elements have to be made using fancy physics. So typically when you're getting into artificial elements, they're made in reactors at places like Hanford. But we're not really going to get into that too much. It's really interesting stuff, though. I think that's where we'll leave it today. Are there any other questions, though, before we stop? Oh, all right. I'll see you guys tomorrow. Make sure that you check out Sapling, and feel free to email me if you guys have any questions.